Okay, I believe we can start while the others will join us during the webinar. So welcome today to this webinar, the potential of computational fluid dynamics for efficient pulse jet cleaning of fabric filters. This webinar will be held by Professor Gianandrea Vittorio Messa, which is standing besides me. Professor Messa is Associate Professor of Hydraulics at the Civil and Environmental Engineering Department of the Politecnico of Milano. Gianandrea is the hosting company. We have committed 1 year ago one study to Politecnico of Milano in order to verify the computational fluid dynamics techniques as a potential model to simulate air and parameters which are involved in the jet pulse cleaning technology in order to better the performances of the support and filter belts. It's a long path, but we already, after 1 year, we came to some conclusions, and we are going towards the future, the development of cages, which potentially could better the energetic balance of the dust collectors. And for this, there will be in future a next webinar where we will present our technical solutions, proprietary technical solutions that we've been able to imagine thanks to the Politecnico of Milano, which is the main engineering university in Italy. So I leave now the words to Professor Messa, and we will share our screen and see you later. We are not answering online the questions because we believe maybe the questions will be not so easy to answer, but at the end of the slide, I mean, during this speech that will last 20 minutes, but of course, there's an email where you can send your questions, both to us or to Professor Messa, and this information will be on the last slide, the reported email address. Thank you for your attention, and please enjoy our webinar.
So, thank you very much for your kind introduction. And as we said, I'm now going to tell you and to introduce you the first part of a research project which started about 1 year ago, and is dedicated to the use of computational fluid dynamics, so CFD, for the efficient handling of pulse jet cleaning technology. And what is pulse jet cleaning technology? So this is a well-established technology for the removal of the dust cake from fabric filter bags. Actually, the working principle is quite simple in the sense that there is a jet of compressed air released from a tank, and the jet creates a pressure wave which travels inside of the bag, and the pressure wave exerts a mechanical action, so a shaking action on the fabric filter, and the shaking action finally causes the dust cake to detach. According to the literature, the cleaning efficiency of pulse jet technology can be related to fluid dynamic parameters related with the traveling of the pressure wave. And particularly, the idea is as follows. Imagine that you focus on a given section Z1 along the bag, and imagine that you want to monitor the pressure history in this section. You have a trend which is similar to the red curve in the top right plot, where the pressure first increases, then it reaches a maximum where when the pressure wave crosses the section, and then the pressure decreases. Now, if you take the local maxima of the pressures for every possible sections along the bag. You build a plot, which is the plot of the peak pressure distribution. So the peak pressures along the bag. And similarly, if you take the arrival times of the pressure wave of the peak pressure along the bag, you build up another curve, which is the curve of the arrival times. The two curves are shown in the bottom right corner of the slide. And according to the literature, basically the higher the peak pressure and the lower the arrival times, the better, the higher the cleaning efficiency. And in order to improve the cleaning efficiency based on this physical and fluid dynamic idea, a well-established technology consists in installing a venturi at the entrance of the bag, because a venturi accepts some sort of suction effect, so it causes more air entrainment into the bag itself, increasing the peak pressures and making the wave faster, so reducing the arrival times. Now, the premise at the basis of this research project, and particularly the first part of the research project, which is described in the present seminar, is that the computer simulation through computational fluid dynamic techniques has a great potential for the engineering handling of the pulse jet cleaning technology. And this consideration mainly arose from the well-known advantages of CFD compared to alternative, more traditional approaches, like, for instance, laboratory testing. Because CFD is able to provide much distributed information of the flow, because you get the map of the velocity vectors, the pressures, the temperature in many points and in many time instants. Moreover, CFD does not suffer from size constraints, in the sense that virtually you can simulate a small system, a big system with comparable computational effort. Then, generally speaking, CFD is less expensive than laboratory testing, but clearly the high cost of purchasing the licenses of commercial CFD code must be always borne in mind. And last but not least, we can say that commercial CFD codes are nowadays very quite straightforward and intuitive to use, in the sense that even if one does not have a great strong expertise in fluid mechanics or computational fluid mechanics, then he or she should be able to obtain in a quite easily manner a qualitatively plausible solution. But the history is completely different if one wants to have quantitatively meaningful results, because this requires a lot of expertise and knowledge and precise protocols to follow. At the same time, CFD is well known to have limitations. So first limitation is due to the fact that the computational simulations are quite time consuming. Just to give you an example, the simulations carried out in this project, which referred to a simplified benchmark case, had a calculation time of about 3 to 4 days. But the computational cost could be even higher for other types of geometries. And most important, a solution of a CFD simulation is affected by several factors inducing uncertainty. So it is highly uncertain in nature due to the many approximations made. And therefore, producing reliable and confident CFD results is a very challenging task. And so, in summary, what we can say is that nowadays, CFD can be a useful tool mainly to identify the directions for research and design. So, to answer questions like, okay, but if I modify the geometry of the system in this way, am I expecting an improvement in the performance or a worsening in the performance? This is something that CFD can help to answer and to address. At the same time, laboratory testing on selected prototypes may be developed on the grounds of CFD results is definitely required before finalizing the R&D process or before releasing new products. And basically, we have said that CFD is characterized by many sources of uncertainty. And broadly speaking, we can divide these sources of uncertainty into two main groups, so numerical factors and modeling factors. Numerical factors are due to the fact that the equations are not solved analytically, but they are solved numerically. And so there are a lot of factors decided by the users, and introduces uncertainty to the CFD results, which relates with the numerical analysis processes. This includes, for instance, the solution algorithms, the difference in schemes, and most important and very important from the point of view of the users, the computational mesh used to discretize the space domain and the time-stepping schemes. But at the same time, we have also modeling sources of uncertainties. And this is peculiar to fluid dynamics, and it is due to the fact that before being discretized, the basic fundamental equations obtained from the physical principles, so mass conservation, momentum conservation, energy conservation, must be manipulated and approximated to be handleable by a computer. And this approximation is not for free because it introduces uncertainty, and it requires the users to make a lot of modeling choices. And so, in a certain manner, the problem is that there is no single way to approximate the equations, and there is no universally best way to approximate the equation, but the way to approximate and to manipulate the equations before discretizing them is problem dependent. All these factors basically produce uncertainty. And we can say that starting from these premises, the main goal of the first part of the research project starting 1 year ago is to make CFD an energy efficient tool for the design of a pulse jet cleaning system and pulse jet cleaning technology. And this basically requires coping with all the sources of uncertainty listed above. So estimating the impact of the different sources, selecting the most critical sources of uncertainty, and properly controlling them. Then we also produced a workflow and the best practices and guidelines for engineers who would like to use the CFD approach for this specific type of application. This opened the way to an exploration of the influence of the geometry of the collar Venturi assembly on the cleaning efficiency, and it will be briefly shown in the very last part of the seminar. But what is in the end the workflow that we proposed? Basically, this is a workflow divided in a pipeline divided in 5 steps to be carried out in sequence. So first, the physical consistency of the CFD solution must be assessed, which basically means just from a mere qualitative point of view, assessing whether the solution is physically sound. Then there will be the assessment of the numerical convergence of the CFD solution, which basically means that it must be proved that the numerical factors producing uncertainty, and so the factors related with the numerical solution of the flow equations, are properly controlled and selected. Then there is an analysis of the impact of the modeling factors, so the way in which the equations are manipulated before being discretized. So, for instance, the turbulence model, the fluid dynamic model, the thermal dynamic model, and so on. And finally, an experimental validation. So basically, with the developed CFD model, the users should reproduce a laboratory test for which experimental data are available, and a good agreement should be found with respect to the experimental evidence. After the first steps described so far are completed, then the CFD model is ready for application, and so it becomes a useful tool for engineering design. And okay, now I will show you an application of the proposed workflow and methodology. And to this aim, reference was made to a simplified benchmark case, which basically mimics a system for pulse jet cleaning technology. And basically, the system comprises a big cylinder mimicking the compressed air tank. Then there is a conical converging nozzle. Then there is the collar Venturi assembly, the filter bag, and the cap at the bottom of the tank and part of the surrounding environment. The benchmark case is axisymmetric, and therefore use was made of a 2D axisymmetric model, which allows saving considerable amount of computational time without affecting too much the accuracy for the scope of the project. As a fluid dynamic model, the compressible formulation of the unsteady Reynolds average Navier-Stokes equations was selected due to the high compressibility of the turbulent air flow. As a thermodynamic model, the ideal gas equation of state was selected. And as for the fabric filter model, the vibration and so the mechanical behavior of the fabric was not solved explicitly, but as it is always and very commonly done in the literature, the fabric was modeled as a fixed cylindrical surface with zero thickness, obeying the filtration law of Darcy to relate the pressure drop to the filtration velocity. The solution strategy was a two stages sequential one. In particular, we have a stage number one, which is called the pulse phase, representing the release of air from the compressed air tank. In this case, the domain is the one shown in the slide, and as you can see, it comprises two zones. One is a yellow zone representing the tank and the converging nozzle, and the second is a light blue zone representing the venturi, the collar, the bag, and the surrounding environment. The duration of the stage number one is equal to the physical duration of the pulse jet phase, which was taken as 0.1 seconds in our study. The solution at the end of the pulse phase was stored and used to initialize the second stage, which is called the travel phase. In the travel phase, there is no more release of air from the tank, and the pressure wave travels within the bag. In the travel phase, the yellow part of the domain, so tank plus nozzle, was removed, was deactivated, and the nozzle outlet was replaced by a solid wall, mimicking the effect of a closed valve. And if you recall, the workflow that we proposed in this research project is divided in 5 steps. The first step is the qualitative assessment of the physical consistency of the solution. And this basically requires answering questions like, is the solution physically sound or in line with the theory, or in line with the fluid mechanics principles? And an example of a verification of the physical consistency of the results is shown here by referring to a specific test case in which the tank pressure was 6 absolute bars. There is no venturi installed upstream of the bag, and the bag is closed with a bottom solid cap. And you can see a lot of color plots here referring to the configuration of the airflow at different times. Particularly, the 3 color plots on the left part of the slide represent the solution at the very end of the pulse phase, so at 0.1 seconds. And we are looking at the part of the domain in between the exit of the nozzle and the entrance of the bag. The top color plot is the velocity magnitude plot, and you can see that the jet is spreading as it leaves the nozzle. The intermediate color plot represents the Mach number, and you see that the values of the Mach number are well above 1, indicating that the flow leaving the nozzle is not only highly compressible, but also very supersonic. And below you can see the color map of the pressure distribution. And here you can identify small diamond-shaped blue part and the blue parts in the very bottom of the color plot. And these are a well-known phenomenon of supersonic air jets. Then the 2 color plots in the center of the slide refer to time 0.5 seconds, where the air jet has stopped and the pressure wave has arrived quite close to the end of the bag. And you can see here the color plot of the pressure, where the pressure peak is associated to the passage of the pressure wave through this section. And you can see that the passage of the pressure wave is accompanied by a velocity wave downstream because the pressure wave puts air into motion. Then on the right part of the slide, you can see in the top part the pressure histories at different locations along the bag. And so Z 2 meters, 4 meters, 6 meters represent the distance from the entrance of the bag. And you can clearly identify the pressure peaks. Then if you join the pressure peaks for all the sections and the corresponding arrival times, you get the 2 curves on the bottom right corner of the slides, which are the most important curves for evaluating the cleaning efficiency. Then the second step is the assessment of the numerical convergence, which basically means demonstrating that the numerical factors producing uncertainty, so the factors related with the numerical solution of the flow equations, are suitable for the purpose. And from the point of view of the users, this basically requires demonstrating that the selection of the time step settings and of the computational mesh are suitable. Now I will show you some results referred to a slightly different test case in which the tank pressure was reduced to 2 bars relative. No Venturi is installed, and in this case, the bag was not closed at the bottom, but was left open. We performed the analysis in 2 steps. So at first, we fixed the computational mesh, which consisted of about 50,000 cells, and varied the time step size from 10 to the minus 4 seconds down to 1.2, 10 to the minus 6 seconds. And for all the 3 time steps, we evaluated the peak pressure distributions and the arrival time distributions, which are shown in the plot on the right part of the slide. And what you can see from this plot is that there is a clear trade-off between accuracy and computational feasibility. Why? Because in principle, one would like to reduce as much as possible the time step, because a smaller time step means higher accuracy. But at the same time, a smaller time step means also longer calculation time. And just to give you an idea of what I'm talking about, you can consider looking at the last column in the table. And in fact, when the time step size was 10 to the minus 4 seconds, in order to simulate 1 physical second of process, one would have to wait for about 8 hours. But if the time step size was reduced to 10 to the minus 5, the calculation time increased up to about 3 to 4 days. Now, if the time step size was reduced down to 1.2 10 to the minus 6 seconds, then the calculation time needed to simulate 1 second using the same machine with 6 processors in parallel could only be estimated equal to 40 days. And clearly, we didn't run a 40 days long simulation. So what we did was to stop the simulation before. But in this case, the pressure wave has not arrived to the end of the bag. And so we had only the peak pressures and the arrival time up to a distance of 2 meters. Based on these findings, we can say that basically a time step size of 10 to the minus 5 here appears the most reasonable choice. But as we said, this analysis was performed by keeping the computational mesh constant. And so we performed another study varying both the time step size and the mesh resolution. And basically the idea was the finer the mesh, the smaller the time step. So we were able to compare 3 other simulations characterized by different combinations of time step size and number of cells. And basically what we can see in the 2 plots on the right is that there is a certain variability in terms of peak pressure. But once again, the combination of 50,000 cell mesh and 10 to the minus 5 seconds appears probably the most reasonable one. And so what is the conclusion and the recommendation that we can provide at the end of this convergence study? Well, we found that basically 10 to the minus 5 seconds as delta t and 50,000 cells as computational mesh was the most reasonable choice. Clearly, this is not an absolute. It holds for our test case, but the combination of settings can change according to the geometry and according to the tank pressure. But apart from that, we can say that with this combination of settings, there is some sort of residual variability in the peak pressure. How can we quantify this residual variability? It's difficult to do that in a rigorous manner, but a simple way to estimate this variability, which is some sort of residual uncertainty, is to consider the area which is spanned by the 3 curves, which is the orange area in the bottom right plot. This is some sort of measure of the residual variability, so the residual uncertainty due to the combination of these 2 numerical settings. Now, one could ask, but is it possible to reduce this variability? Well, yes, but this would require performing additional simulations, reducing the mesh and the time step. And this opens up questions regarding and concerns regarding the opportunity of reducing this variability. Because one question is, okay, but would this be feasible? And I would say probably not, because the computational cost with this combination of settings is already 3 to 4 days, which is quite long. Reducing the time step or increasing the mesh would cause even longer simulation times. And the second question is, but would it be really necessary to reduce the variability? Once again, it depends. It mainly depends on the scope of the simulation, because if the scope of the CFD study is to accurately estimate the peak pressure or the arrival time in a given location for a specific configuration, then one should control as much as possible all the sources of uncertainty. And so in this case, I would recommend performing additional simulations. But in our case, the purpose was different, because the goal was mainly to compare different configurations. So the scope was mainly comparative. And if the scope is comparative, probably some residual uncertainty is also acceptable. And so in this case, I wouldn't recommend running additional, more time-consuming simulations, and this is what basically we did. Then, step number 3 concerns the analysis of the impact of the modeling sources of uncertainty. As I said before being numerically discretized, the fluid dynamic equations must be manipulated and approximated, because otherwise are not solved because of the high computational cost. And so the users must make some modeling choices, and these modeling choices relate to the fluid dynamic model, to the thermodynamic model, and to the fabric filter bed model. For the fluid dynamic model, for instance, one could decide whether to model the fluid as compressible or incompressible, but in this case, there was no doubt, because the jet released from the nozzle are highly compressible. But another important problem is how to model the turbulence. It is well known from the literature that there are 3 main approaches, so RANS, LES, DNS, and within every framework, we use the RANS because this is the preferred approach in engineering computations. The users must select the turbulence model and the near wall modeling approach. And for the thermodynamic model, one should decide the equation of state of the gas, and also the configuration of the energy conservation equation. And in the case of turbulent flow, also the closures for modeling the turbulent heat flux in the RANS framework. Finally, regarding the fabric filter model, one possibility is to model explicitly, to resolve explicitly the vibration of the bag induced by the wave. But this is never done, because it would lead to unacceptable computational cost. And therefore, we decided, as it is often done in similar problems, to model the bag as a porous surface with imposed permeability law. And the point is that all these factors are choices that the users must make, and they affect the reliability of the results. And how it is possible to select these parameters, submodels, and settings? One possibility is to rely on the literature, so on previous CFD studies, and we did it. Another possibility is to rely on the theoretical and physical knowledge of the process. And a last possibility is to rely on experimental data if they are available. And in this case, the match with experimental data can serve as a criterion to decide the modeling settings. Now, I will show you very briefly a sensitivity analysis on 2 important modeling parameters. And these parameters were selected because they are particularly critical in the sense that they are difficult to decide. The first parameter is related with the modeling of the turbulent flow. And what we did basically was to focus on a single test case, which was the same of the convergence study. We considered a given section which is quite close to the entrance of the bag, and here we monitored the peak pressure and the arrival time. The first modeling feature that we analyzed is the turbulence model, and particularly we compared the solution obtained with K epsilon realizable, scalable wall function, and no compressibility effects, with the solution obtained with K omega SST turbulence model, including a compressibility effect. You can see in the blue bar plots that there is a considerable variability in terms of peak pressure and a certain variability in terms of the arrival time. And so how we decided the best option? Well, we selected K omega SST with compressibility effects because we said, okay, clearly the flow is highly compressible here. And so we expected that including compressibility effects on the turbulence in the turbulence model would be scientifically sound. The second modeling factor was the permeability coefficients of the fabric filter bed. And what we did here was to make a literature review, considering the values of this permeability coefficient analyzed in previous study. We investigated the entire range, focusing on the two extremes, which are 10 to the minus 7 square meters and 10 to the minus 13 square meters. And we saw that basically the peak pressure and the arrival time in the probe location were not affected by the value of this coefficient. And so what we claim is that we expect a minor influence of the permeability coefficient. And here we must note that this is not an absolute. Clearly, the answer and the impact of the permeability coefficient is restricted to the specific test case that we analyzed and to the specific probe location. Maybe if one changes the probe location or changes the testing condition, there is a greater impact of the permeability coefficient, but at least this was a good starting point. Then, step number 4 is the experimental validation. Basically, the purpose of the experimental data is to verify by comparison with experimental data that the configuration of the CFD setup, and especially all the modeling features, is suitable to obtain predictions in line with some experimental evidence. This is essential for any CFD simulation. And basically, the best way to go would be to dispose of in-house experimental data so that the case is the very case of interest for the campaign. And moreover, by performing in-house experiments, one has all the necessary information to reproduce numerically the laboratory test. This is the best way to go, but clearly it requires disposing of a facility, of experimental equipment, and of experimental know-how. Another possible way to go, if one does not have experimental data available, is to refer to cases reported in the literature referred to similar scenarios. This is basically what we did because in the first stage of the research project, we didn't have in-house experimental data. So we decided to reproduce numerically a test case reported in the literature, which was quite similar to the one of interest to us, but with an important difference, because in the experiments reported in the literature, a Venturi was installed at the entrance of the bag. In our CFD simulation of the experiments, no Venturi was installed, and this was mainly done for reasons of time and opportunity at the stage of the project. Anyway, by making this comparison, we can see that the peak pressure at a selected location along the bag, estimated by our CFD, is about 25% lower than the experimental value. Based on some consideration, we can say that a similar underestimation can be acceptable because it might be due to the fact that in our simulations, no Venturi was accounted for. Probably accounting for the Venturi and including the Venturi in the CFD setup would reduce this underestimation to a very small value. Clearly, this is a bit speculative, and it is reasonable but speculative. And indeed, now what we are doing and what we are planning to do is to improve this validation by reproducing the most closely as possible the experimental test by Liu and Shen. And finally, after completing these first 4 steps, we are ready for the application. So the CFD model has been properly established, and therefore it could be applied for investigating, for instance, the effect of the geometry of the collar Venturi assembly on the cleaning efficiency through the analysis of the peak pressure distributions, the arrival times, and we also monitored the amount of air entrained into the bag during time. So we are now ready to come to the conclusion of this seminar. And basically, what we did in this study, which is the first part of a research project started 1 year ago, was to assess, the goal was to assess the potential of CFD for the energy efficient design of pulse jet cleaning technology. But actually, we could say that the scope of the part of the project described in this webinar was mostly methodological in nature. And indeed, the main goal was to propose a pipeline of steps to be undertaken to get confidence in the CFD results. And we also provided some best practices and recommendations to other engineers who would like to use a CFD for this kind of application. Finally, in the last part of the webinar, we showed very briefly that once it has been properly established, the CFD setup can be used for making a design optimization in an energy framework of the system. And last, the findings obtained in this preliminary study have been complemented by a prosecution of this research project, and the company which supported this research, so Linear Europe, took advantage of these results to develop activities of R&D and product development.
So, thanks to Professor Messa for this, I hope, but I believe also interesting, very interesting webinar about the potential of computational fluid dynamics in our industry. I hope that you have enjoyed. Of course, it is possible to reach us for any questions at info@linearworld.it. In this slide, you can also find references of the team of the people that participated to this document. This document was also introduced the very first time at FieldTech 2023, last February in Germany, in Köln. And unfortunately, that time, Professor Messa was locked with the problem of airplane in Munich. So we gave him back the possibility to reply. Our effort towards, we have stated energy saving cages. That's why what we have, how we have referred our project to our application will be continuing. We'll be continuing, and we will soon come to the market with some concrete applications that will permit to save energy of the fan and of the compressor, or increase the air inlet in dust collectors. Clean Air, of course, works towards a path of sustainability, which involve to consider energetic balance of the dust collectors. So thank you once more. Thank you to all for attending this webinar. I hope you enjoy. We keep it in touch. Thank you.